Now, you will all have experienced performance issues while building apps. You may have spent hours or even days developing ways to push processing out to separate threads, or just to work out why an activity indicator doesn't show. In this lesson, I'll go through some of the solutions to these issues. Let's take a look at threads. What are threads? Threads make it possible to execute multiple code segments within a single app, often concurrently. Concurrently is the key word there, and we can think of threads as multiple pipes through which different pieces of code can be executed at the same time. The phrase multi-threaded implies that you have to create and manage multiple threads in order to get the performance benefits of running concurrent operations. The system manages the threads once you've created them and schedules them across the available processors and resources, juggles them as needed, and running different operations across multiple threads can improve an app's perceived responsiveness and no doubt will improve its performance. But managing threads within an app can be very complex, and it's not easily scalable, it's not easy to manage, and it's not easy for the operating system, the underlying operating system, to know how many threads you've opened in your code, how many you've created, and what to do with them. So you'll give yourself a lot of work when you start to look at coding multi-threaded applications. Fortunately, iOS offers alternatives to threaded programming, one of which is Grand Central Dispatch, which allows you to define dispatch queues to execute either serially or concurrently, and dispatch sources which submit blocks of code to a queue for execution whenever an event occurs. Another feature of iOS are operation queues. Operation queues are Objective-C objects that act very much like dispatch queues, and you define the tasks you want to execute, and then add them to an operation queue which handles the scheduling and execution of the tasks. And operation queues use the NS operation queue Cocoa class. We'll come back to them in a moment, but let's look at some other alternatives to threaded programming, such as asynchronous functions. Now, various Cocoa Touch frameworks use asynchronous functions, for example, asynchronous network functions, instead of synchronous ones. Idle time notifications, timers, or separate processes. Now, one example of a separate process may be a web service, if applicable, that uses server processing power to perform a task, which the app then presents results from. In this case, you'd have to think about network latency as being an issue, but it may be possible to post a request off to a server to show the user something else on the interface, and then to present the results of the calculation from the server response at a later point in time. The aim of all of this is to improve perceived responsiveness. What is perceived responsiveness? It's ensuring that your main thread is free to respond to user events, so that you don't block the user interface while you're waiting for a file operation to finish, for example. And that's essential for a good user experience. Nothing says this app is broken more than a frozen user interface. Now, if you provide a loading indicator or a loading text or something, then the user's going to know that your app is doing something, and they're going to wait. Also, if you're using an asynchronous approach, you're posting a request off to a server, a user can continue to work, and your app will receive the response from the server and in the background quietly save data or whatever is necessary without locking up the user interface. That is a much better responsiveness experience. Now, when we're looking at improving responsiveness or perceived responsiveness, we need to design concurrency into the application from the very beginning. It's not something we can go along and add later without reworking an awful lot of not only code logic, but also design thinking. We should identify tasks that should be encapsulated in operation queues, and then they can be coded up as operation queues at the development point. So how do operation queues look? As I stated before, we have the NS operation queue class. It's Objective-C based. And we have an NS operation class, which can have dependencies or priority and can also be cancelled, should we wish to cancel an operation or give the user the chance to cancel an operation. And it supports completion blocks and execution state monitoring, which means we can at any point get feedback from the operation queue about whether it's running or whether it's finished. If you don't use an operation within an operation queue, you can specify an operation and you can specify it to be started, and it will by default be synchronous. Another type of operation queue is the NS invocation operation class, which creates an operation from an existing selector and object within your application. You may have code to process particular events already written within your application, and you can effectively repurpose this and reuse it to create operations. NS block operation will create an operation using one or more blocks within the application. NS block operations implicitly support a group semantic. That means you can have several blocks added to an NS block operation, and the operation will work through all blocks added to it in sequence. Once all blocks have been completed, the operation is then complete. So let's take a look at how you define an NS invocation operation. Here we have a custom task. We have a myTask selector, which is performing our application logic, our task logic in this case. And we can simply say, within our taskWithData method, create a new NS invocation operation called theOp, associate it with a selector, myTask, passing through data that's passed into the particular function here. We take a look at the NS block operation. To create one, we'll simply define it as a new NS block operation, in this case again called theOp, and associate it with a block. Inline block declaration, very straightforward. Now you'll typically add at least one block at initialization time like this, and you may add more blocks as needed later on. To add more blocks to the NS block operation, you will simply use the add execution block method. So let's look at how you define an NS operation. You'll create an NS operation with custom init, main and dealloc methods. The dealloc being to release objects created within the operation, as these may otherwise be left hanging. And you can add support for cancelling and monitoring by overriding the isExecuting, isFinished and isConcurrent methods. Typically, isConcurrent will return yes to define a concurrent operation, and if you're running an NS operation outside of an NS operation queue and you want it to run concurrently, then you will return isConcurrent yes. Now we'll come to an example of creating an NS operation in one of the lessons in this chapter. But for now, that was our look at threads and concurrency. Further information about threads can be found within the developer portal, as can information about concurrent programming. I would recommend the Concurrency Programming Guide as an extremely good read and the most important thing you should read on this subject. It will take you more through NS operations and also cover Ground Central Dispatch, which I won't be covering in this course. If you wish to understand more the low-level concepts of multi-threading and threads, then take a look at the first document. But remember, the aim is to improve perceived responsiveness. Anything you can do to ensure that your application loads quickly, retrieves data in the background as needed, carries out intensive operations in background threads or separate threads or in server processes, uses timers, uses feedback to the user, whatever is necessary. These are the most important things about improving perceived responsiveness and will make your application not only perform better, but also seem to perform better.